If you're able to hear me, just say yes. If not, you probably would not say anything. Okay, so thank you. We're gonna start lecture 5 right now, lesson 5. And lesson 5 is 5 and 6, they're very similar. So if you understand 5, you're gonna understand 6. And we're gonna do a few exercises. So at the end, hopefully 5 and 6 will be easy lessons.
Sir,
Yes.
did you take attendance?
Not yet.
Okay.
Not yet. So we will have an introduction, then we'll take the attendance. Okay. So these, I'm gonna introduce this lecture by doing this. So let's have that we have two circuits. This is one of them. So two networks. So this is a network here, has two terminals. I'm gonna give those some values here, 4 ohm. And this resistance is a 12 ohm. This is 8-volt source. And this is 32-volt source. And this is 5 ohm resistance. Okay, so this is one circuit. Here's another circuit. Those are the two terminals, same as those terminals. And this is 8 ohm resistance. And this is 16-volt source. Okay, so look at these two circuits. Which one of them is the easier circuit to analyze? Left or right? Which one of them is a simple circuit compared to the other one?
Right.
Yeah, the right one has two elements. So if I connect, for example, I call it load here to this circuit between those terminals, and I say this RL is, for example, 2 ohm. And I ask question, what is IL in this? So what is this current? And I give this question to someone and I say, okay, find IL. And please do it within 2 minutes. And I do the same thing to this person and I say, okay, I'm gonna give you that same load. And I say, okay, 2 ohm, find IL here. Now I'll give you the option, find either one of them. Either this or this, which one is easier to find? Probably this one is easier, way easier to find, because this one is just the voltage 16 divided by the total resistance, which is 8 plus 2. So this is 10. So this is 1.6 ampere. See, this circuit is easier than this. If someone wants to find the current here, you're probably going to spend 10 minutes or 5 minutes or something to find it, and you have to do mesh analysis or nodal analysis or something. And this is even not complicated. Circuit can be more complicated, but guess what? The current here is the same, 1.8 ampere. So this is if RL equals to 2 ampere, 2 ohm. What if I change RL and make it this RL? That's changing. And I'm gonna make it, and instead of this, I'm gonna make it 8 ohm. And I say, okay, RL is 8 now, find IL. It's gonna take you time to do the calculation again with the new resistance, but if I do it for this circuit, IL, it will be like, if this is 8 plus 8, so it's 16 divided by 16 equals 1 ampere. This is for RL equals to 8 ohm. This is for RL equals to 2 ohm. Okay, so I'm just gonna erase this one and erase this part. So RL is changing, let's say. The load is changing. This is for RL equals to 8. And you're gonna get the same result here, 1 ampere. Now, I'll get the same result when I connect the same loads. What does that mean? It means this and this are the same. So when I connect the same resistor, I get the same current. I connect 2 ohm here, I get 1.6. I connect 2 ohm here, I get 1.6. I connect 8, I got 1 here. I connect 8, I got 1 here. If I connect other value here, will be the same as this one. But the difference that this is an easy circuit to analyze, and this is not easy. Not very easy at least, or not as easy as this one. But these two circuits are called equivalent. This and this, they're called equivalent circuit. Why? Because when I analyze them, the load resistance, the load current, the load voltage is going to be the same. Equivalent. So this circuit is equivalent to this. So instead of analyzing it here, I'm going to analyze the easy one. I'm going to work on the easy one and find what I want instead of working on the difficult one. But the problem is if you have the difficult one only and you don't have the easy equivalent circuit to it. So what is the thing here? So the thing is to find easy equivalent circuit to the difficult circuit. And this is our topic today. So the topic is basically this. If you have a difficult circuit, or at least not the easy circuit, and this circuit, you need to do something with it all the time, like load is changing or something is changing here. So you want equivalent circuit. So I want equivalent circuit to this circuit, and it's an easy circuit. So I want what I call equivalent circuit. And this equivalent circuit is easy as one source and one battery. So for this circuit, this is the equivalent circuit. But what is the value of this resistance, and what is the equivalent, and what is the value of this source? This is our topic. So the topic here, this lesson, is finding circuit that is equivalent to complicated circuit. So easy equivalent circuit easy equivalent, it means easy to analyze. Okay, for what? For complicated circuit. So some complicated circuit, I'm gonna find an easy circuit that's equivalent it for a complicated circuit. Now, what is the easy circuit? Only one source and one resistor in series. This is a very easy circuit. Now you have bunch of resistors. You're going to find one equivalent for them. And you have one source, and sometimes you have, you have two sources here. Sometimes you have 10 sources. You're going to find one source that is equivalent to those sources. Then you can say this circuit is equivalent to that. Whatever that circuit does, this will do the same thing. So it is equivalent circuit. Now, the guy who came up with this technique or idea of finding a small or easy equivalent circuit is called Thevenin. So that's his last name. So this equivalent circuit is called Thevenin's equivalent circuit. Okay, this circuit. And now, because of him, he is the one that found that, we don't call this R equivalent and E equivalent. What we call them R Thevenin equivalent and R E Thevenin equivalent. So the lesson 5 is called Thevenin equivalent circuit. And that is basically a simple circuit of a source and resistance. And this circuit is equivalent to a big circuit. Why do we do this? Because it's easier to analyze the simple circuit rather than analyzing the complicated circuit or the bigger circuit. Sometimes the circuit has 20 resistors and impedances and stuff and has 10 sources, current sources, voltage sources mixed all together. So it will be really nice to actually have a simple equivalent circuit to that complicated circuit. Is this okay so far? Just the concept? What is this all about? Any questions here? Okay, so now what we're gonna do, we're gonna see how can we find this equivalent circuit. So we call it Thevenin equivalent circuit. So the way to find it, okay, if I want to find this, it means I have to find two things. What is R Thevenin and what is E Thevenin? Because this is the equivalent circuit. I need to know what is R Thevenin and what is the E Thevenin. For this circuit, R Thevenin is actually 8 ohm and E Thevenin is 16 volt. This circuit and this circuit are equal. You connect any resistor here or any resistor between those two terminals, you're gonna get the same current. 100 ohm here, 100 ohm here, you're gonna get the same current. But how do we find this 8? How do we know it's 8? How do we know it's 16? That's the question. So two things. R Thevenin is the equivalent resistance when we have no sources. So no sources. We only want the resistance. So you're going to remove the sources from the circuit. E Thevenin is the open circuit voltage. So if you bring a voltmeter between these two and bring a voltmeter, so I'm going to open this, a voltmeter between these two, what you read here should be the same as here. Okay, what you read here is V open circuit, because now it's an open circuit here. It's going to be the same reading here. And because this reads the same voltage as this one, so this equals to E Thevenin. So what is E Thevenin? Is the open circuit voltage. Now someone would say, why the reading of the voltage here is equal to this voltage? Okay, Here's example for this. The voltage here is 12 volt. What is the voltage between these 2 points, here and here? It's going to be 12 volt. Why is that? Because it's an open circuit, no current. Current is 0. If there is no current, the voltage across here is going to be 0 volt. So basically, if it's a 12 volt here, it's going to be 12 volt here. You're not losing or gaining anything. So you guys have a lab at 5:30 at the college? You're
Yes,
supposed. So you should be here before that so you can attend this in here, like in campus. Not be a good idea to drive during the lecture. Okay, so I'm gonna continue and I'm gonna go to the lecture. This lesson is another circuit analysis, so it will need practice. So Thevenin's theorem, what does it say? It says any circuit, any network, linear network. Linear network means has current sources or voltage sources, inductors, capacitors, resistors. Those are linear elements. It means the voltage and the current have a linear relationship. Sometimes you have amplifiers, you have transistors. Those ones are not linear. So this network, theorem is not going to work. Okay, but for us, it's going to work all the time. We don't have amplifiers, we don't have transistors, we don't have non-linear devices. So it says any network, it doesn't matter how big the network is, has 2 terminals. Here can be so many things: resistors, capacitors, inductors, connected in so many sources, connected in any way. This network, the big network, has 2 terminals. This network can be replaced with equivalent circuit, an easy equivalent circuit. That equivalent circuit is just a voltage source in series with a resistor. That's it. So I can find the equivalent circuit for this complicated circuit. Now, resistor, if it's an DC, sorry, and if it's AC, we call it impedance. So if it's AC, we use just impedance here, call it Z Thevenin, and we use a source that is AC source, like that. So this is Thevenin equivalent circuit in the AC. This is Thevenin equivalent circuit for the DC. One more time, what this theorem says: any network has 2 terminals. You have to have terminals in the network. If you don't have terminals, then you cannot look into the network. It will have equivalent circuit, only voltage source and resistor connected in series. This circuit is equivalent to that. It means we'll do the same thing. Anything you connect between these 2 terminals and you connect it between the equivalent circuit, you're going to get the same current and the same voltage and the same power. It means what this circuit does is exactly equivalent to what this circuit does. Now we're going to go through what is the procedure. The first thing to do that, okay, my job is I have a circuit, a network. It has 2 terminals, this and this. I want to find the equivalent circuit for this circuit, the same terminals. So first thing, RL, whatever between the 2 terminal is not included in my circuit. So I don't do anything with this, just leave it. So this is just out. The second thing, I need to find R Thevenin. The third thing, I need to find E Thevenin. Then I'm gonna draw the circuit. You have to draw the circuit. If they give you the network and say find the equivalent network, you have to draw the network. Okay. So how to find R Thevenin? Not difficult. R Thevenin equivalent. Now there's dependent sources. This case is not applied for our course. You never did dependent sources. You don't know what they are, but they're electronics more than electrical. So how do we calculate R Thevenin? We remove the sources. It means we set the sources to 0. How do we set the sources to 0? So if I have a voltage source, this gives me voltage. How I can make the voltage 0? I replace it with a short circuit. V equals to 0. If I have a current source, this gives me a current. How can I set the current to 0? I replace the source with an open circuit. Means the current is 0. So, because I only want to calculate the resistance, I have to remove the source's effect. Means I have to set the sources to 0. The voltage source, I'll make it 0 volt when it is a short circuit. The current source, I make it a 0 when it's an open circuit. So, in another word, voltage source is replaced with a short circuit. Current source is replaced with an open circuit. Then you just find the total resistance. So this is how you find the total resistance. We're going to practice that. Now, how to find E Thevenin? Basically simple. E Thevenin is just the open circuit. So you have to have the sources in the circuit. Don't remove them now, because you're going to find the voltage. It is the open circuit voltage. It means between the terminals. You leave them open and you try to find what is the open circuit here. This open circuit voltage, it's the voltage at the terminals, is actually the equivalent voltage or the Thevenin voltage. Once I have R Thevenin, I calculate it, calculate E Thevenin, I have to draw the circuit. This is the last thing. I have to draw the circuit. Any questions? Any questions? With exercises, it will look fine, hopefully. With exercises, it will look fine. Okay. Okay, here's an example. We're going to find the Thevenin equivalent for this network, the shaded network. So it means this network. First of all, this network has 2 terminals, and everything inside is linear. That means I can actually find Thevenin equivalent circuit. Those are the 2 terminals. Step number 1. I'm going to remove this. This is not included. This is the load connected to the network, not included. Okay, that's step number 1. I removed it. Those are the 2 terminals. This is my network that I want to find the equivalent for. The second thing, I need to find R Thevenin. How to find R Thevenin? We're going to remove the effective sources. Voltage source, we replace it with a short circuit. Then between the 2 terminals, find the total resistance. Now, if you want to do it in a lab, you can just measure the resistance between here using an ohm meter. But for us, as a calculation, you're just gonna calculate these 2 resistors connected in parallel, and you can see that they're actually connected in parallel. So 3 and 6 connected in parallel is 2. That is R Thevenin. So I know the equivalent circuit will look like this. This is the equivalent for this circuit. Okay, and this is R Thevenin. and I found it, it's 2 ohm. This is the load here connected, which is, this is not part of my, I still need to find E Thevenin. Then I can say this circuit is equivalent to this circuit. Now to find E Thevenin, it's the open circuit voltage. Here what we have. So I'm gonna leave the circuit open and try to find the voltage. Now this is the open circuit, okay, between these 2 points. This is E Thevenin here. So the voltage between these 2 points, the terminals, when they're open, it's E Thevenin. And now this point is exactly like this point. And this point is exactly like this point. And this is an open circuit, so they're not affecting. So this circuit is basically exactly like this circuit. The same thing. And E Thevenin is the voltage just across the 6 ohm. So how to find this voltage? You can use the voltage divider because you have a source, 2 resistors in series. So you can use the voltage divider. Or you can just find the current, which is the current here is 9 volt divided by 3 plus 6. The total resistance is 1 ampere. So 1 ampere is here. The voltage across the 6 ohm is actually 1 ampere times the 6 ohm. Ohm's law. It's IR. 1 and 6, so it's 6 volt. So using Ohm's law or using the voltage divider, I can actually find the open circuit voltage. But remember, it is the open circuit. It's the voltage between these 2 points when they're open. And this point is exactly like this point, the same voltage. So this is like A, and this is like B. It's the same point. So this is like my A, and this is like my B. So I found the R Thevenin and I found E Thevenin. Now what I should do, I should give them the equivalent circuit. I should draw it. So this is the equivalent circuit. So for that circuit, this is the equivalent circuit. Now, once I have the equivalent circuit, if I want to do circuit analysis, it's easy. So if someone says the resistance here is 2 ohm, find the current. It's pretty easy. But if you go in the first circuit, it's a little bit complicated to find the current. Here it's easy, just 6 divided by 4. If the resistance changes and becomes 10 ohm, so it's 6 volt divided by 12, 2 plus 10. So the analysis of the Thevenin equivalent circuit is very easy. You can connect any load here. I can find the current very quick. I can find the voltage very quick. I can find the power very quick, I squared R. Very quick. But if you go to the original circuit, and by the way, even the original circuit is not very complicated. This circuit, if I say this is 2 ohm, it will take you some time to find the current here. It will take you some time. You have to combine the resistors, then find total current in the current divider, or use the mesh analysis or nodal analysis. But if you can find the equivalent circuit, then it's really easy to use to find the current. So finding equivalent circuit is usually for equipment like motors or generators or network or something that you find the easy equivalent circuit, so you can use it whenever you want to do analysis for the different loads. We're gonna do another example, which is this one. Okay, here's a network, has 2 terminals. That's a condition. The network has to have 2 terminals, and you want to find Thevenin equivalent. So at the end, Thevenin equivalent will be like this: 1 and 1 source. And now will be like this circuit is the equivalent circuit to this circuit. Those are the terminals A and B. Those are the terminals A and B. So this is equivalent to this. But I have to find what is R Thevenin here. and what is E Thevenin. So at the end, I can say, okay, I can analyze this simple circuit instead of analyzing this difficult circuit. So first thing, I have to make sure that there is nothing between A and B. Remove whatever in there. It's already removed, there's nothing. The second thing, we're gonna try to find R Thevenin. Okay, R Thevenin, how do we find it? We remove the sources, the effective sources. We only want resistors in the circuit. So voltage source we replaced with the short circuit, so it's 0 volt here. Voltage source we replaced with the short circuit. This is what we have. Now this resistor, the 4 and the 12, they're connected in parallel. You combine them, you get 3. So 12 times 4 divided by 12 plus 4, this gives you 3 ohm. So once these two are combined, the 3 ohm, you have the 8, and these two are combined into one resistor, which is 3. So the total here is 8 plus 3, it's 11. I found R Thevenin. I need to find E Thevenin is the next thing. So I found this value. I write it here. E Thevenin, I can use the nodal analysis if I want. I'm gonna use the nodal analysis on this side because I just like nodal. Or I can use the voltage divider as well. So the nodal analysis, I can find the voltage at this point. So this is their node. This node here is my 0 volt. And there is this node Vn, this one here. There are 3 branches connected to this node. 3 branches, right? Okay, I'm gonna assume the currents are leaving here and here and here. So the entering current equal to 0, the leaving current, there are 3 of them. So the first current going this way is Vn minus the voltage here, 32. The voltage minus the voltage gives me the voltage across the resistor divided by 4. 32 divided by 4. Then the current going down in R2 is Vn minus 0 divided by 12. Then the current going this way, what is the current going this way? What's the current, the third current going that branch? Can anyone tell me what is the current going in that direction to the right? Okay, other attempts, please. It's actually 0 because it's an open circuit. The current cannot go through. Current cannot go through an open circuit. So there is no current going this way. So when you solve this equation, you're going to find Vn equals to 24 volt. You can find it using the divider here between this resistor and this resistor. Anyhow, so I'm going to clear this, and the voltage here is 24 volt. Is there current going here? No, 0 current. Because it's an open circuit. So what is the voltage across this one? 0. The voltage across this resistor is 0 because the current is 0. Remember, voltage is I times R. This is the voltage across the resistance. Now, if the voltage here is 24, what is the voltage at this point? If it's 24 here, what is the voltage here? Any answers? Now, why 12? Here's one more time. No, not this. I'm going to give it the source. The voltage here is 24. What is the voltage here? Okay, if this is 10, it's 14. See, this is positive, this is negative. You go from 24, you want to reach this point, you're going to lose 10 volt. You go from positive to negative. This 10 volt is actually 24 minus 14. 24 minus 14. So the voltage here, if it's 24 volt here, the voltage here is 10. Sorry, 14. Is this okay, the idea that the voltage is a difference? It seems that, as I said this several times, you did the whole course in this last semester, and it seems it's still that you don't know that the voltage is a difference. So someone says the voltage between here and here is 10 volt. If the voltage here is 25, it means the voltage here is 15 because it's the difference between the 2 points. 10 is the difference between the 2 points. This is the positive side, this is the negative side. 25 minus 15 give me the 10. So if you go this way, you lose 10. If you go this way, you gain 10. 15 plus 10 is 25. 25 minus 10 is 15. Building like this, this is the 10th floor. This is the 25th floor. The difference between them is 15. This is the voltage, the difference. If you go up, you gain 15. If you go down, you lose 15. Voltage is the difference between two levels. Please try to keep that in mind. The voltage is a difference. If someone gives you the voltage here 24, you should be able to find the voltage here because you know the difference between here is here and 10. So this is 14. Okay, what is the voltage at A? This is 0 volt because there's no current here. What is the voltage at A? So if there is no loss here and no gain, 0 volt. So this 14 is going to be the same as this 14 here. If you don't change the voltage level, you stay at the same level, 14 and 14. What is the difference between them? Is 0 volt. There is no voltage here. Why there is no voltage here? Because there is no current. Why there is no current? Because it's an open circuit. So the voltage here is 14, the voltage here is 0. What is the voltage between this point and this point? The open circuit voltage. 14. So if the voltage here is 14 at this side, the voltage here is 0. What is the voltage between them? Which is the open circuit voltage, is the difference, 14 minus 0. It's 14. So E Thevenin is 14. R Thevenin, we calculated 11. This is the equivalent circuit. This circuit is equivalent to this. This is the original. This is the equivalent. See, the equivalent is very simple. It's just one source and one resistance. This is called R Thevenin equivalent. This is E Thevenin equivalent. R Thevenin is the total resistance when we remove the sources or set them to 0. E Thevenin is the open circuit voltage, the voltage between these 2 points. We're going to do this one exercise, then I'll let you go. Okay, so find the Thevenin equivalent circuit for the network to the left of the terminals A and B. You have to have terminals. So this is what I want, an equivalent circuit to this. And these are the two terminals. So, and it's Thevenin equivalent and it's a DC circuit. So what is going to be the Thevenin equivalent? It's going to be this. This is the equivalent circuit to that one. And I want to find this equivalent circuit. R Thevenin, E Thevenin. And at the end, this is A, this is B, and this is the load connected, which is changing here. Now the load is not part of the circuit. It's not part of the circuit. So it's added to the original, it's added to the equivalent. This is equivalent to that one in the box. So my job is to find the equivalent circuit. Once I find the equivalent circuit, I can use it to do the analysis instead of analyzing the original circuit. So this is my ultimate goal at the end, to find this circuit. It means to find R Thevenin, E Thevenin, and draw the circuit. Now, first thing I'm going to try to find R Thevenin. So when we find R Thevenin, what do? We remove the sources because we only want to find the resistance. And the voltage source, we set it to 0 by a short circuit. Current source, we set it to 0 by open circuit. So these are the terminals, A and B. We're going to find the resistance equivalent between them. Resistor, a resistor, source, a resistor here. Then this goes back here, and we have a source here. This is 1 ohm. This is 4 ohm. This is 12 ohm. And this is whatever. So what I'm going to do, first thing, I'm going to remove the sources. So this source is gone. This source is gone. The current source, I'm going to replace it with an open circuit because I want the current to be 0. Set it to 0. The voltage source, I'm going to replace it with a short circuit, so 0 volt. So this is the first step. I only want to find R Thevenin, so remove the sources. Now I'm going to make it look nicer. Open circuit is not going to affect my circuit, so here's what we have. This is how this circuit will look like. This is the 1 ohm. This is the 12 ohm. This is the 4 ohm. This is R Thevenin. Now I'm going to do these two are connected in parallel, and the equivalent for them, 4 and 12, connected in parallel, so I multiply, divide by the sum. It's going to give me 3 ohm. Another way to do it, you can do 1 over 4 plus 1 over 12, and it's going to give you 3 ohm as well. Two ways. So 3 ohm here. That is this part for this box. Then the rest is still the same. This is the 1 ohm, and this is R Thevenin. So now what is R Thevenin? Two resistors connected in series, it's 4 ohm. So this value is 4 ohm here. almost done with my circuit because I draw the equivalent circuit. I find R Thevenin. I'm like 60%, 70% done here. I need to find E Thevenin, then I'm done with the equivalent circuit. Is this okay so far? Like finding R Thevenin is fine. The Thevenin equivalent resistance. Any questions here? Okay, now we're gonna try to find E Thevenin. Okay, E Thevenin is the open circuit voltage. So I'm gonna have this. As I said, I like nodal analysis, so I do nodal most of the time, but you can do other techniques to find it. Whatever technique you want and you feel like it would work, branch analysis, mesh analysis, okay? Kirchhoff's voltage law, dividers if you can use them. Probably you can't here, but it's up to you. Now I'm gonna put the circuit with all sources. I'm done with R Thevenin, okay? And this is E Thevenin between these 2 points. So I'm gonna use the nodal analysis, okay? But as I said, you can use other techniques. So nodal analysis, this node is my reference. I'm gonna say V0. Anything connected to it is gonna be the same voltage, like this, and like this, all here, 0 volt. Then this is a node. I'm gonna call it V1, or let's say V1, okay. Anything connected to it will have the same voltage. So even this node here is the same voltage. I don't have nodes anymore. So the node 1 here, there are 4 branches connected to it. So the sum of the coming current equals to the sum of the leaving current at this node. Now any current coming, yes, the 2 ampere is actually going to the node. Now this is like one node. There's 2 ampere going to the node, so coming is 2. Now I have 3 other branches. One current is leaving this way, one is leaving this way, and one is leaving this way, and this one here is coming because it's given to me, it's coming. So I'm gonna use the first one. Find the first current, Ohm's law. Voltage cross the resistance V1 minus 32, because it's 32 here. And at this side is V1, the current is going from V1 to 32, divided by the 4 ohm, plus the current in the 12 ohm, voltage across divided by the resistance. So what's the voltage across? Positive here, negative here. This side is V1, this side is 0. So the difference between V1 and 0, that is the voltage across 12 ohm divided by the resistance gives me the current. Plus, this is the third current leaving. It's going to the open circuit. So what its value is 0. Open circuit current is 0 current. There is no current. Current cannot go through an open circuit. Now I can solve this by multiplying by 12. For example, to get rid of the fractions. So this is 24 equals to 3 V1 minus 3 times 32 is 96 plus V1. You solve this equation for V1 and 120, so it's 30 volt. I want to find E Thevenin, not just the node. So the voltage here is 30. The voltage at this point is 30. What is the voltage at this point? It's the same, 30. The reason it's the same because there is no current here. There is no drop in this resistance. There is no drop in this resistance. So the voltage at this point is actually the same as the voltage at this point. And what is the voltage here? It's actually 0 because it's connected to this one. So E Thevenin is actually 30 minus 0, so it's 30 volt. Okay, so I got to this, it's 30 volt. I'm done with the Thevenin equivalent circuit. They're saying once you have the equivalent circuit, RL, give it 6, 10, 30 to find the current. So if RL equals to 6, I'm going to put 6 here. The current IL is going to be just 30 divided by 4 plus 6. So it's 3 ampere. And you can find it when RL equals to 10 is the second one. Then when RL equals to 30, it's pretty easy here, IL. So it's in the simple circuit, it's very easy to find the current. Now, if it's this circuit and someone says, okay, find the current when RL is 10, then it's a problem. You're going to spend a lot of time doing the analysis. But the simple circuit, the equivalent circuit, so this is actually Thevenin equivalent circuit. So when it's 10, this is 10 and this is 4, so it's 14. And this is 30. This is like 2.14 ampere. Then you can do it for this one as well. Still 30 and 4 plus 30. This is like 0.88 or something ampere. You can look at this here, take a screenshot. I'm gonna do the attendance and let you go. I know you have a lab. It's crazy that some of you are actually coming to the lab right now. But if you have classes, come early. You're allowed to come to the college early and you're allowed to be here ahead of time. So you can come to the college. And I think if there is an opening next week, like we can have students during classes, maybe we can have this class here. Maybe we can have this class here. Okay. Try to review this. We're gonna do more exercises tomorrow morning. Try to do the assignment. Assignment 2 is on D12. Okay, so I'm gonna just go to the attendance. Quite quick. Today, which day is 24th? Okay, Abdullah, no, wait. Okay, the names are just flipped here. Yazan,
Yes.
Isam Makki, Abdullah Hassan. Isam is not here. Abdullah.
Sir, I'm here.
Okay. No, that is Abdullah. That's not you, I think. Abdullah Hassan.
Yes, sir.
Okay. Lean. Yes. Asia.
It's me.
Okay. Muhammad Abdurrahman, yes.
Yes.
Rand, Amal,
Yes.
Hazim, Manal, Abdullah Ahmed, Khalid Ali, Ahmed Al-Tayyib, it's not here. Sarah, okay. Maryam Ahmed,
Here, mister.
thank you. Hassan,
Yes, sir.
Samar, yes.
I'm here,
Um,
sir.
Sharif, yes, thank you, Sarah. Sharif,
Sir, I'm Samar.
Samar. Actually, Samar, yes, thank you, Samar. And Sharif, no. Hamad,
Yes, sir.
Abdullah Khalid. I think Abdullah Khalid is the guy who just said yes at the beginning.
Yes, yes, I'm here, sir.
See, I told you that name is not you, Abdullah. Asma. Asma. Thank you. Fahad. Awatif. Abdullah Ali.
Yes.
Ahmed Ayman. Muhammad Yusuf.
Yes.
Ziyad Ali. So here's the names that we don't have. So we don't have Isam Makki. We don't have Abdullah Hassan Ad-Dawali. We don't have Hazim. We don't have Abdullah Ahmed. We don't have Khalid. We don't have Ahmed Al-Tayyib. We don't have Sharif. Not Fahad. Not Awatif. And not Ziyad Ali. Everyone else is okay. Thank you guys and best of luck with your lab. And I'll see you
Sir,
inshallah. Yes.
you are in the college?
Yes, I am.
Okay.
You need
Okay,
something,
sir,
you can come here.
okay. Thank you, sir.
Okay. Classes until now there are actually online all the time, but we will wait and see what will happen next week. So the classes are online for now. But next week we don't know. I don't know yet. Probably they're online, still online, because we did not get any email or anything. Okay, I'll see you guys inshallah tomorrow.